This first one here, this first piece here, I'm just going to remind you what a complex number is. Complex numbers come in the form a plus bi. This a piece is just a real number, okay? This bi is the imaginary component, okay? So this is the imaginary part. So every complex number has a real part and an imaginary part, and either one of those parts could be 0. So if you think about that, then any number, like 6, like 3.2, can be seen as a complex number because the imaginary component is just a 0, okay? Now, when we plot complex coordinates, it's one complex number, but because there's 2 pieces to it, we can plot on a complex plane one single complex number. So looking here, this is the complex plane. You can see that if in our minds, the x-axis is the real axis and the vertical axis is the y, or the imaginary. So to plot 2 minus 3i, we would go 2 in the real direction and then minus 3 in the imaginary direction, and that is the coordinate point for the complex number 2 minus 3i, okay? Now, things to note about this. When we have a complex point, like this, we can calculate the absolute value of a complex number. In the absolute value of a complex number is its distance to the origin. So the absolute value, I'll call this z, the absolute value is going to be the distance from the origin to that complex number. And we usually use Pythagorean theorem to find it, okay? Which is what this box is telling us. Hey, a squared plus b squared, or in other words, x squared plus y squared is equal to the hypotenuse squared. Well, you'd solve it by doing a square root, okay? So for this next example, it's saying, hey, here's your complex number, find the absolute value of it. Well, I like to do a visual. So this is in my reals, this is in my imaginaries. So we're going to go a positive root 5, and then we're going to go down 1. So this is where the plot is for that complex coordinate is right there. And if we want to know the absolute value, we're going after this distance right here, would be the absolute value of this number they're calling z. Well, Pythagorean theorem then. Absolute value of z squared, right, is equal to, jumping the gun, root 5 squared plus 1 squared. In other words, the absolute value of z is equal to, we're going to square root. And we got to do order of operations, right? The inside stuff has to happen first. This will end up being a 5 plus 1. So the absolute value of z is root 6. And we're done. That's the distance it is from the origin. Okay, same thing here, just to review. 3 in the reals, negative 4 in the imaginaries. This right here is our point, but the distance from 0 is the diagonal here. So a squared plus b squared equals c squared. A squared is 9, b squared 16, c is equal to the square root of 25, which is 5. It really wasn't a c, was it? The c this entire time was the absolute value of our complex number z. There's the answer to that. Okay? All right. Now, we have seen regular coordinate points, the rectangular coordinate points, not complex. Let's go over here for a second. Not complex, okay? X, Y, rectangular Cartesian coordinate point, okay? When we converted it to polar, it looked like what? R theta. polar, not complex, okay? That's the rectangular, that is the polar form for non-complex numbers. When we do complex, it's going to look different. Complex numbers in rectangular form are, you have your real part plus your imaginary part, which is in front of an I, okay? That is what we would consider the rectangular. And when we write it in polar form, it's going to look different yet. And that's what this box is telling us. It's going to look like, at the end of the day, this one. Okay, so rectangular, polar. Radius times the cosine of theta plus I sine of the same theta. There is the polar form for a complex number. Okay, and it all depends on whether or not we're looking at a complex or a non-complex. Okay, all right, let's go back here. This top stuff is stuff you already knew, right? Like how to find the radius out, what x is equal to, what y is equal to. Okay, that stuff doesn't change. So here we have the complex number 4i, and we want to convert it to polar coordinates. These first couple of examples are actually pretty easy, and then we'll get to more complicated ones after that. First example, 0 in the real directions, 4 in the I direction. Right there is 0 plus 4i. Now, in polar coordinates, right, I can already see that the radius here is 4. We would get this as 4 for the radius out from center times the quantity cosine pi over 2, because it's straight up, plus I sine pi over 2, because it's the same angle. This is your polar coordinate, okay, as a like the complex number as a polar coordinate. Okay, let's do the same thing for this next one. Again, giving you an easy example here. -4 in the real plus 4 in the imaginary puts that coordinate point right there on a polar grid. On a complex grid. Now, how do I convert this? Well, I'm going to lightly make this a triangle. 4, 4. I can find the r by doing Pythagorean theorem. So the radius out is going to equal the square root of 16 and another 16, which is going to be 4 root 2 when we clean it up. Okay. Now, that's the radius out. I also need to know the angle. Well, if you remember your unit circle quite well, if the two sides are the same, then this is a 45 and a 45. So in other words, in radians, this is going to be 3 pi over 4. So at the end of the day, we have a complex polar equation of z equals 4 root 2 times the quantity cosine 3/4 pi plus I sine 3/4 pi. Now, I've had students in the past like calculate 3/4 pi and sine 3/4 pi, but if you calculate those and then simplify this expression, you literally are going to end up with -4 plus 4i. So it kind of takes you full circle. So you have to know when to stop. So when you have the form, you stop. Okay? Okay. Which leads me into this very next one, and that is when we have this in polar complex form and we want to go to rectangular form, this means I want it to look like a plus bi or x plus yi, right? We literally just simplify. Cosine of pi over 6, hopefully you know your unit circle well. Cosine of pi over 6 is root 3 over 2, if it'll let me write. Sine of pi over 6, we have your I here. Sine of pi over 6 is 1/2. And we just simplify. Distribute the 12, we'll get 6 root 3 plus 6i. There's your complex number in rectangular form. Okay? All right, so let's go to this next one. Find the rectangular form for this complex number. All right, so here's what we know. We want the rectangular form, so this is what we want, endgame. We know r, and we know tangent to theta. This is interesting because the form that we can get, the polar complex form, will look like r times cosine theta plus I sine theta. The issue is we don't know theta. But I would challenge you to think, do you really need theta? They're telling us that the tangent of theta is 5/12. Remember, tangent of an angle is opposite over adjacent. So I don't actually need to know theta. I can use Pythagorean theorem and find my radius. And now that I have that, which actually we already knew the radius was 13, silly me. 13 cosine, it's 12 over 13. Sine is 5 over 13. Distribute your 13. 12 plus 5i. That is in the form that you wanted.